Into your break this morning, so apologies in advance. So bear with me as I provide a bit of an update on some of the activities that have been going on related to PEER and funded by PEER for the Next Generation Liquefaction project. It's quite likely that many of you have heard about NGL for some time because the project was initiated back in 2014. And quite frankly, I'm a bit of a newcomer after having only interacted with NGL for about 2 years or so. But in general, the project is led by the project management team, including John Stewart, Steve Kramer, and John Snematikos, advised by senior geotechnical professionals in the field. It includes various efforts, including database development, focus studies, and model development. One thing that sets this project a bit apart is that there are many modeling teams set within the community environment, working from a common database to develop various models to deal with liquefaction hazard assessments. I'm not going to spend a lot of time on this particular slide, but these slides will be included after the meeting for you to download. I do encourage you to investigate the various tools and resources that have been developed as part of the liquefaction NGL project. So when a geotechnical engineer professional begins a liquefaction hazard assessment, they generally follow a three-step progression. First, let's make an assessment of the liquefaction susceptibility. In other words, could liquefaction happen given sufficient loading? The next step is, will liquefaction be triggered under a particular design loading? And the third step is then to evaluate the consequences, perhaps in terms of outright instabilities or displacements. The NGL project seeks to unpack susceptibility from triggering, and then the triggering of liquefaction from manifestation of liquefaction. In other words, the evidence or consequences of liquefaction. And so the PEER Research Center has certainly aided NGL to advance this particular goal. So with that, in addition to overview of some database efforts, I'll provide an update on some of the activities at NGL that are funded by PEER. One of the first activities I'd like to talk about was a workshop on liquefaction susceptibility funded by PEER that was held approximately 1 year ago at the Oregon State University campus. This included 50 international participants, drawing from an array of academics, practitioners, and government agency representatives. The report is particularly dense. It explains how the organizing committee established the workshop. It presents the results of a pre-workshop poll. It goes in particular depth describing the discussions that were held over 3 distinct sessions, answering key prompts put forth by the organizing committee, and discusses several key items that I'd like to just briefly chat about. But I'd just also like to point out that there are numerous extended abstracts from participants in the workshop that provide an excellent wealth of information, as well as all the slides are available for download for presenters at the workshop. So one of the key items that participants discussed focused on how we should approach the first step in the liquefaction hazard assessment, that is, assessments of liquefaction susceptibility. Should these assessments consider material properties only, such as the mineralogy or the plasticity of the materials, or should they consider characteristics of both material and state? Certainly, there were a wide array of opinions expressed at the workshop, and I think that's something that we weren't quite able to resolve in perfect unanimity. The second key item rests upon terminology and usage of available liquefaction susceptibility criteria. On one hand, folks seemed to understand that liquefaction susceptibility may be a term that can just focus purely on behavior, specifically hysteretic behavior, and whether a material can ultimately bring about a complete loss of strength and stiffness, versus another viewpoint in which assessment should be driving engineer towards a particular evaluation tool for cyclic strength, which serves up into the second aspect of liquefaction hazard assessments. And the preferred term proposed for that was cyclic strength evaluation criteria. Again, there's an entire chapter devoted to key item number 2, and as well as with key extended abstracts that explore this in detail. The third key item, which is what I want to focus on the most, are the research needs identified by the participants and summarized by the organizing committee. So One of the research needs culminated in a vision in which next generation liquefaction susceptibility models could be developed. These models should predict whether fundamentally granular behavior or sand-like behavior will or will not occur. This is aligned with the material susceptibility concept I mentioned earlier. And the models should also be probabilistic in nature so they can be folded within the current NGL formulation for liquefaction hazard and manifestation assessment. In order to meet this vision, we identified that a database focusing directly on liquefaction susceptibility ought to be developed. Such a database should call in georeference explorations with co-located CPT and borehole data. Laboratory data should include cyclic test data, preferably monotonic test data. Those tests should be performed to particularly large strains in order to identify identify ultimate hysteretic behavior, that is, whether it's sand-like or clay-like, perhaps identify strength normalization, and of course all sorts of related metadata index test data to support susceptibility model development. Such a model should also identify and treat sources of epistemic uncertainty. These sources of uncertainties could be due to regional differences, either geomorphological or in practice of conducting explorations. Certainly there are differences in interpretations of hysteretic behavior that leads to epistemic uncertainty, and naturally the functional form of whatever model a modeler decides to use to characterize liquefaction susceptibility probabilistically. So in order to meet the vision and scope identified by the workshop participants, several proposals were put forth to peer and were selected for funding over a 2-year period with partial student support. And these projects initiating in fall 2023 seek to directly address the research needs that were identified in the workshop. So let's move a little bit forward into how NGL is treating liquefaction hazard assessments, but first we can consider maybe a traditional approach in which observation of liquefaction in the form of cracks, sand boils, settlements, these are forms of manifestation, were set equal to the fact that liquefaction was triggered. Likewise, if there was no evidence for liquefaction, we traditionally have said, well, liquefaction wasn't triggered. The NGL approach is likewise probabilistic, as many recent models are in the literature, but uses a prior probability based on laboratory cyclic test data that then gets fed into manifestation models, which are trained or referenced to case histories in which manifestation was or was not observed. So this approach allows rational consideration of cases where liquefaction was triggered, but there was no evidence. The classic example is a deep liquefiable layer, which may have achieved excess pore pressures of 100%, but there was no evidence for it at the ground surface. So in this case, the fact that no manifestation had occurred is not entirely equal to the fact that triggering did not occur. On the other hand, it also allows for manifestation even if liquefaction was not triggered, albeit a low probability. So within the current NGL framework, the probability of liquefaction triggering, given that manifestation was observed, is calculated considering 3 probabilities. The first is the probability of manifestation given that triggering has occurred. The second is the probability of manifestation without triggering. These essentially represent the manifestation models, which are informed by case histories within the NGL field case history database. And then the third component is the probability of triggering prior to incorporating the case history data. With the new work that we're proposing, we can address a prior assumption, which inherently, because the prior probability for triggering was based on laboratory cyclic data of largely sandy soils, which are susceptible to liquefaction, so the previous assumption could be associated with a probability of susceptibility of 1.0. Instead, we can consider various data sets from the literature. I've got an example of these data sets up on the right-hand side, but there are numerous other publications that can be drawn from, as well as the new NGL peer susceptibility database, in which we see that there is some uncertainty in the characterization of susceptibility, either from a material-based point of view with PI on the upper right-hand corner, or CPT-based assessments where we might use the soil behavior type index I sub C. And this is particularly important for transitional soils, which span a broad range of materials of continuously fining material that will eventually transition into non-liquefiable, depending on mineralogy, plasticity, and perhaps other factors. So our goal is to harvest the data in these data sets, reference the field data to laboratory cyclic hysteretic behavior, in which the ultimate hysteretic behavior associated with a sand-like or clay-like behavior can be adequately characterized, and then develop susceptibility models probabilistically and assess the sensitivity of these models to various inputs and assumptions. So the functional form of our updated NGL model will replace that prior probability of triggering to include the probability of the material being susceptible. So that's where we're going under the framework of the new peer-funded NGL projects. The last thing I wanted to talk about, and it turns out I've made up a little time there, that's good, is a separate peer-funded project that was not directly associated with NGL at the time, but will be incorporated as we move forward. And that deals with transitional soils. The cyclic resistance of these materials are particularly difficult to evaluate. Number one, low plasticity silts with a soil behavior type index smaller than 2.6 are not well represented in the pre-NGL liquefaction case history databases. On the contrary, soils with soil behavior type indices greater than 2.6 were often excluded from pre-NGL databases. Also, penetration resistance is often complicated in these materials due to poor pressure generation during sampling or penetration exhibiting partial drainage. And so these kinds of materials are your silty, clayey sands, your sandy silts, your silts and clay silts. The examples of data shown on the right-hand side indicate that these transitional soils exhibit a transition in cyclic resistance, going from relatively small cyclic resistances for your non-plastic materials to very low plasticity to increasing cyclic resistance as plasticity increases. But in addition to cyclic resistance, they show a transition in strain development and excess pore pressure development. And so that just has presented a complication moving forward. To show just how complicated it can be, let's consider clay-like soils which exhibit cyclic softening. We've got moderately PI materials in red with soil behavior type indices that would often be considered non-susceptible. We can see that Shansep-based cyclic resistances, shown in the black marker compared to the open white circular marker there, are excellent. Okay, the errors are within 5%. So materials which are strength normalizable and are clay-like seem to be well predicted in terms of their cyclic resistance using available methods. If we look at sand-like materials, which include non-plastic silts and very low plasticity, let's say a lower bound PI of 5, in which CPT-based liquefaction triggering procedures are appropriate based on model developers, we can see that the cyclic resistances are dramatically underestimated, on the order of 50% or greater for some of the data sets we've studied at Oregon State University. And so that indicates that the lack of, or the sparsity of data in that region based on these legacy triggering models has a direct influence on our ability to make decisions on liquefaction hazard assessments. Of particular concern are the transitional soils that are low plasticity, maybe PIs of 10 to 15 or so, in which the CPT-based triggering analyses are just inappropriate, so don't use them. But also the Shansep procedures are not particularly good either, and that's because these materials aren't strength normalizable. And so this provided us our motivation for doing the work under 2023-01, which culminated in the development of a suite of models, basically empirical cyclic resistance models, that take into account the plasticity of the material, the stress history through the overconsolidation, and can provide estimates of cyclic resistance for a range in strains from 1 to 10% shear strain, which is fully compatible for future incorporation within the PBE framework. And so I've just got some examples of model output for different ranges of plasticity and stress history, as well as examples of the strain-dependent nature of cyclic resistance. This report also includes updates to models for estimating the number of equivalent cycles and associated magnitude scaling factors for the subduction zone earthquakes, which also should serve to improve our estimates of liquefaction cyclic softening in general particularly in the Pacific Northwest. The results of this work has several applications. It looks like I'm just about out of time, so quickly, this facilitates preliminary assessments of the factor of safety against cyclic failure, will allow practitioners and researchers to plan cyclic testing programs, and allow folks to calibrate constitutive models in the absence of site-specific cyclic laboratory test programs. So with that, peer-funded research has certainly aided to advance critical areas in liquefaction hazard assessments. This has culminated in several reports, as I've described here, as well as continued expansion of the NGL database, both for field case histories and liquefaction susceptibility models. Over at the NGL, that database, as I mentioned, continues to expand. We've got multiple community teams that are working together in an open and transparent process to develop differing models that address or take advantage of different aspects, or let's say intensity measures. And the supported modeling team within the NGL umbrella continues to improve their probabilistic models, separating triggering from susceptibility as well as from manifestation. So thanks so much for your attention, and I guess we can now go to break.